Welcome to this course on optical communications. In this module we will continue the discussion of optical transmitters. We have looked at the representation of signals both in continuous time domain as well as we have introduced the geometrical viewpoint of visualizing the signals in the last modules. We will utilize that theory here to discuss various digital optical modulation techniques. The word optical is used because we are talking about optical communications, otherwise this material is essentially digital modulation techniques. Now it is always possible, or at least in most cases it is possible for us to communicate by means of digital data. That is, we can think of the simplest communication way is that of communicating via symbols 0 and 1. So let us say for some reason, some magical reason, our alphabet is reduced to two symbols. These symbols can be denoted as 0 and 1. So let us say I denote these symbols as 0 and I put this inverted comma here to show that this is a symbol. This is not the number that I am representing, this is a symbol, okay. And then 1 is a symbol. I mean, a familiar example would be the English alphabet. You have in the English alphabet a total of 26 letters, right. So from A to Z. Similarly, we have in our hypothetical source, we have two letters 0 and 1. Together with this forms an alphabet, okay. So this is not English alphabet, this is some sort of a binary data alphabet which has two symbols 0 and 1. Just like the regular English alphabet has 26 letters, these letters are essentially those symbols A, B, C up to Z. We do not put the inverted commas because we kind of understand what alphabet and letters are. So this is the analogy by which we want to proceed. So we will assume that our alphabet consists of 0 and 1, and whenever a transmitter communicates some information to the receiver, it will communicate by sending a sequence of such symbols 0 and 1, right. So for example, in some message the sequence of symbols might be 0, 1, 1, 0, 0 and so on. Let us say the last symbol is 0. This is, let us say, n such letters were used, and since each of these letters we will eventually see that they can be represented in terms of binary digits, this is called as a n bit sequence or an n bit string, okay. Of course it is not yet become a string, it will become a string when we assign this 0 to the number 0 and 1 to number 1, okay. So far this is kind of a letter sequence. So it is possible in most cases to reduce any complicated information or any general kind of an information. It could be speech, for example, it could be the video that you are actually viewing now, right now, it could be the text that someone has written. So all these different kinds of sources, they are all coming from different sources, they can eventually be represented, or they can be represented by this sequence of zeros and ones. A familiar example is, how do I represent this letter A in ASCII code? ASCII code consists of 7 or about 8, I am not very sure, but it consists of a sequence of zeros and ones, though number zeros and ones or the symbol zeros and ones, which will then allow you to write down all these different letters. So if I want to send OPT from the transmitter to the receiver, I will substitute this O with the corresponding ASCII code for O. I will substitute here the corresponding ASCII code for P, and here will be the ASCII code for T. So I can substitute each letter which is actually originally in English by that particular sequence which is made up of those zeros and ones, okay. So in this way I can reduce any information that I want to transmit into a sequence of binary symbols. These are all the symbols, these are the binary letters. So we can reduce them to binary letters. Why do I call this as binary? Because there are only two possible letters. So bi corresponds to 2. So binary stands for 2, and there are these two symbols which are labeled as 0 and 1, okay. Now what we do is, this is of course the letter, this is how you would, for example, write on a piece of paper. But if you want to transmit, or on a computer you would type OPT, and internally the computer converts this OPT into sequence of zeros and ones. But remember, this sequence of zeros and ones are just the symbols, or they are the sequence of letters. They are not the numbers, they are not something that can be transmitted directly over the transmission medium. For example, I can't take a symbol 0 and then transmit directly the symbol 0 on the optical fiber. I have to convert these zeros and ones into an appropriate form that is suitable for transmission over the fiber channel. Okay. And this process of taking these symbols, which are essentially abstract in nature, and converting them into forms which are suitable for transmission over the fiber optic cable, or in general any transmission medium, is called as the modulation. So you can think of modulation as some sort of a matching mechanism, wherein the symbols which are abstract and they cannot be communicated directly over the channel are being matched to the form in which they are suitable for transmission over the channel. Okay. So this is the binary communication, and what we will be looking at today is how can we consider this sequence of symbols and then come up with waveforms which will be transmitted over the fiber optic channel. Okay. So to do that, let us first give some waveform representation for the symbols. Okay. So I have a symbol 0, and let us say I denote this one by sending a pulse, an optical pulse for example, of duration t seconds. Okay. So this is the optical symbol. So we do not have to name what this one is, so or we want to name, let us call this as some g of t. So this g of t waveform, actually having an amplitude, let us say 1, will be transmitted over the optical cable. Okay. So this waveform g of t would represent the symbol 0. So we say that this 0 is represented by this waveform. So if you are someone who is looking at the time varying waveforms, the moment you get this pulse, you can say that, oh, the transmitter is trying to send a symbol 0 to me. Okay. So that is how you would know the mapping from the symbol to waveform. Okay. So this mapping from symbol to waveform is, of course, this is decided by you. You could, for example, go in the conventional way and say, I do not want to transmit a pulse, but I will transmit nothing during the duration for a duration of t seconds in order to represent the symbol 0. So this choice of whether transmitting a pulse, or the pulse need not even be of this shape, someone might actually say I will transmit this pulse, right. So the kind of waveform representation that you give for the symbols is determined entirely by you. Of course, you have to be consistent. You can't use the same waveform to represent two different symbols, then there will be problem, right, because you look at the waveform and you won't be able to tell whether you have transmitted a 0 or a 1. So you avoid that simple pitfall, and you are completely free to choose whatever the waveform that you want to transmit. So let us, for simplicity's sake, in this course, or at least until this module at least, call this rectangular pulse, the pulse which is equal to 1, having an amplitude of 1 for a duration of t seconds, as representing bit 0 or the symbol 0, and then this symbol 1 will be represented by transmitting nothing. Okay. So we will represent 1 by transmitting an amplitude 0 over the duration of the symbol, this one. Okay. So this t, which is the duration over which the waveform is representing a particular symbol, is called as the symbol duration. Okay. If this 0 is mapped to a binary digit, that is numerical 0, and if the symbol 1 is mapped to a binary number 1. Okay. So this is a symbol, this is a number. Okay. To denote the difference between symbol and a number, I have used the inverted commas. So if you use 1 to denote the symbol 1 and 0 number to denote 0, this 0 and 1 is the binary digit. Okay. Each of them is called as a binary digit, or short for bit. Okay. So a bit 0 is represented by a waveform which is a rectangular pulse having a duration t seconds and an amplitude of 1, and bit 1 is represented by an amplitude of 0 for a duration of t seconds. Okay. So this is what my waveform representations look like. Now these waveforms, are they ready to go on the optical fiber? Well, not quite yet, because we have these waveforms in what is called as the baseband domain. Okay. In the baseband domain, the frequency content is mainly concentrated at the 0 frequency. Okay. But if you want to transmit this symbols, or these waveforms over optical fiber, what you would have to do is to transform this baseband into what is called as pass band or band pass sometimes. Okay. So, you want to transmit this into pass band. The immediate question you might ask is, why should I do that? There are various reasons. First of all, by transforming them into pass bands, right, you can allow more than one user to transmit symbol in the optical fiber at the same time, right. So, I have user 1 here who wants to transmit a sequence of 0, 1s and so on. Remember, now this is a bit sequence which I have written, which means that you have to mentally substitute for each bit here the corresponding symbol that is shown here. Okay. So, there is user 1 and there is user 2, okay, and both want to transmit information. If they both are allowed to transmit in the baseband, then the information gets jumbled up, right. You can't separate them out. Rather than allowing such a possibility, what you do, and you got nothing, what you do is you assign a certain frequency to this person, you attain another frequency to this person. Okay. So, to this person who is transmitting U1, you assign a frequency of FC1, to the person U2 you assign a frequency of FC2. That way you are allowing more than one user. Of course, you can continue this provided that FC1, FC2 and all the other frequencies are sufficiently far apart. Okay. Now, the simplest way of transforming this baseband into passband is to recall a theorem in Fourier transforms, right. If g of t is a signal which has a Fourier transform of g of f, then if I multiply this g of t by e to the power j2 pi fct or equivalently by cos 2 pi fct. So, this is the real way, this is the complex way. So, if I multiply by cos 2 pi fct, you know that this has a Fourier transform components which will be centered at fc and minus fc, right. So, this will result in the Fourier transform being centered at fc and minus fc. So, clearly what you have done is to take this low pass signal, okay, or the baseband signal and convert this into a pass band signal whose frequencies are now centered at plus fc and minus fc. Is that okay? Right. So, we know that we have to transmit not in the baseband but in the pass band, but how can we even represent this signal, this sequence that we are, someone is transforming, how do I represent that sequence? Okay. So, I can represent that sequence by writing down the signal in the baseband domain, and I will call this as SBB of t. This would represent the fact that a sequence of zeros and ones are being transmitted, okay, with the basic pulse shape of g of t, right. If you go back to what these symbols or what these bits equivalently were represented by, 0 was represented by a rectangular pulse of duration t seconds, right. 1 was represented by the same rectangular function of duration t seconds, except that its amplitude was multiplied by 0, right. However, for 0 the amplitude was multiplied by 1. So, you have the same basic pulse shape. This rectangular function of t by t is what we had called as g of t. We will assume that this is the case for this module. Then if you have this g of t and multiply this g of t by 1, you are transmitting bit 0. If you take g of t and multiply it by 0, amplitude becomes 0 and then you are transmitting bit 1 or equivalently symbol zeros and symbol 1. So, how can I write down the sequence of symbols? Well, let us just consider a hypothetical sequence that has been transmitted or that we want to transmit 0 1 1 0. To transmit 0 at the beginning of the transmission, you will have to transmit a pulse of duration t seconds, right. It will last from 0 to t. At the end of this pulse, you have to begin transmitting the next pulse, okay, or the next bit. The next bit will be 1. So, where this bit ends, or this waveform ends, the next waveform starts, which would represent bit 1 or symbol 1, and this will also last for a duration of 2t seconds. Next, you want to transmit 1 again. So, the amplitude for 1 is in our representation 0. So, you simply continue, although you know that this actually has ended the transmission for this symbol, you continue this because the waveform is the same waveform for the next bit as well. So, it was 0, this pulse 1, this amplitude 0, next is also 1, therefore, the amplitude continues to be 0. At the end of, so this starts from t and ends at 2t, the symbol 1 starts from t and ends at 2t, the third symbol starts from 2t and ends at 3t, These dotted lines are simply used to show the boundaries, okay, they do not really exist as part of the waveform. And finally, when you want to transmit 0, you start the transmission at this point, right, with an amplitude of 1. So what you have is essentially this signal g of t, and what about this signal? This signal will be 0 into g of t minus t. Would that make sense? Yes, because g of t minus t corresponds to a signal which has been shifted in time by t seconds, right. And what about this third symbol? That would be 0 into g of t minus 2t, and finally the fourth symbol is basically 1 into, so let me also put a 1 up there, 1 into g of t minus 3t, okay. Of course there could be a sequence and that would never end. In general you get the idea, right. In the nth time slot, okay, in the nth time slot where n starts from 0 and goes all the way to the infinity, the time durations are from n t to n plus 1 into t, right. You can check that this is true for this particular example. For example, n is equal to 0, the time duration is from 0 to t, which will then have the bit, corresponding bit will be represented as say an, okay. An can be 0 or it can be 1, right. So by this way you are actually able to represent this waveform. So this would be the baseband waveform that has been transmitted, and this baseband waveform can be represented as a sequence of pulses, okay, whose basic pulse shape is g of t, but then this basic pulse will be shifted by every t seconds, and at every time slot it gets multiplied, the amplitude of g of t gets multiplied by this sequence an, right. So this is how I would represent the baseband signal, but as I said I am not interested in the baseband signal, I am interested in the passband signal. So for the passband signal I will not use any subscript to denote the passband signal, I will use s of t. This can be written as, if you go back to the modules earlier, we had shown how to represent the passband signal, right. So you can represent this as square root of 2 cos 2 pi fct, this would be the carrier, and the square root of 2 is used just for normalization purposes, okay, to normalize the energy of passband signal as well as its complex envelope representation, something that we covered in the previous module. So this is the basic carrier, and then to this basic carrier you need to multiply this pulse sequence, okay, and there is a relationship that you have to satisfy with respect to fc and t. You want fc and t to be some multiple of 2 pi, is that okay. So this would be my passband signal s of t. You can see that the sequence an, right, multiplying the time shifted pulses g of t will determine the overall envelope of the signal, right. If you actually look at how the signal would look like, you know, if this for example would represent a voltage signal, okay, or it could represent the electric field coming out of the optical transmitter, right, it would be this one. So you will have for, you know, initially, because an for the same sequence 0 1 1 0, you will have a fast varying carrier waveform, then followed by a 0, followed by another 0, then again you will have the fast varying waveform. Of course you have to understand that this cycles which I am showing would not even be visible if you were to kind of measure the electric field, which you will not be able to, but if you were to able to measure the electric field you won't even be able to see these cycles, because the frequency for optical communication is around terahertz, okay, which is 10 to the power 12 hertz, whereas the time durations are typically in the order of, time durations or equivalently the data rate is in the order of about say gigahertz. So there is gigahertz is 10 to the power 9 hertz, so which means that in this time slot, if you assume that this is 1 picosecond corresponding to 1 gigahertz, right, there would be about 1000 cycles here. So you won't be able to even see this particular carrier cycles. I have used it just to show kind of an exaggerated version of this. Okay, so coming back, we now have equation for passband signal s of t, and what you can observe here is that the amplitude of the carrier is getting changed or it is getting modulated by this sequence an and this rectangular pulse g of t, correct. More importantly, when an is equal to 0, you have a carrier, full carrier field, and when an is equal to 1, you have the carrier frequency, and when an is equal to 0, you have nothing, right. Or we have taken the convention that a bit 0 would represent a non-zero signal, right. So when an is equal to 0, I do not want the amplitude of the signal to go to 0, but rather I want the waveform to be present. So I can't directly, if I call this sequence as an, then I cannot directly use an here, right. Rather than that, I should be using, so here I will make a correction to this, what I should be using is 1 minus an, so that when an is equal to 0, the amplitude 1 minus an will be equal to 1, and that gets multiplied to the pulse shape, and you get this sequence from 0 to t, and when an is equal to 1, bit an is equal to 1, 1 minus 1 will be 0, and then it would be representing the bit 1, okay. So there is couple of points that you have to remember. The bit or the symbols are 0, 1, 1, 0, and the corresponding amplitudes are 1, 0, 0 and 1, okay. This was a convention which I have followed in this module. You can of course follow the more natural convention that when an is equal to 0, the amplitude of the pulse will be 0, and when an is equal to 1, the pulse will be equal to 1, okay. In that case you will get signal which would look like this. It would be 0 here, followed by a 1, 1 and a 0. The reason why I have seem to have chosen a very different kind of a way to represent this signal is because in the optical transmitter it is natural to realize a 0 to a signal and 1 to no signal, okay. So for that reason I have used this format, but you are free to interchange this format as well as what you want. So going back to this one, 1 minus an is again a sequence. So when an is equal to 0, 1 minus an will be 1, when an is equal to 1, this 1 minus an will be equal to 0. So I can very well call this as sum bn, right. So in place of an I am now going to use this sequence bn, so let me make that substitution here as well. I will be using bn. What is the nature of bn? When an is equal to 0, bn is equal to 1, and this corresponds to, in the waveform, this corresponds to waveform being present, whereas when an is equal to 1, remember these are the bit sequences or the symbol sequences, bn will be 0 and waveform will be absent, okay. So that would correspond to the notation that we have been so far using. So I can write down the passband signal s of t as the carrier that is getting multiplied by a number or the sequence bn. For every nth time slot, this carrier gets multiplied by this number bn, and this bn decides whether the carrier has to be turned on or turned off. So in a sense what you are doing is, with this bn you are turning on or turning off the carrier, right, the carrier being square root of 2 cos 2 pi fct. So you are choosing to turn on or turn off depending on bn is equal to 1 or 0. Here carrier will be on, carrier will be off in some sense, right. It is kind of a switch you are taking and then doing, turning the switch on and turning the switch off. You turn the switch on, carrier will be connected to the output line. You turn the switch off, the carrier will be disconnected to the output line, to the fiber line. Such a modulation technique in which the carrier waveform abruptly changes from kind of being on to off is called as on off keying, because its amplitude is the one which is changing. The amplitude of g of t, or equivalently this square root of 2 cos 2 pi fct, is getting changed to 1 or 0, or rather to root 2 and 0. Because this amplitude is the one which is shifted, this kind of a modulation is also called as amplitude shift keying. The keying should tell you, the key kind of a thing, piano kind of a thing. So you press that key down, you are connecting the switch, and the input, the carrier is connected to the output line. You remove your hand from the key, the switch is disconnected and the carrier is turned off from the connection between carrier to output line. So this is the so called on off keying or the amplitude shift keying modulation formats, okay. So these are the modulation formats called on off keying or amplitude shift keying. Okay. You can think of this on off keying and amplitude shift keying as a general transmission, okay, as a general amplitude modulation. Modulation is basically changing the characteristic of the carrier in order to represent the data. In our case, data is a bit sequence 0 or 1. So, for 0 you give some amplitude, for 1 you give some amplitude. So, essentially you are doing amplitude modulation. Okay. In general, let us say this is the waveform that you want to communicate. Okay. This is the waveform that you want to communicate. Call this waveform as some g of t. Okay. This would then be given to an optical AM transmitter whose carrier output or carrier amplitude would be changed according to this signal. Okay. Instead of having any general variation, our digital modulations have a very strict variation of zeros and ones. Okay. So, that is all the connection between amplitude modulation and ASK. ASK is kind of general or a special case of amplitude modulation.